A swarm of starlings moves mysteriously across the sky. Ants in large numbers are hard to beat in terms of efficiency. Logisticians use the same principles. Myriads of migratory birds move across the Wadden Sea. Swarms of honeybees follow pheromone trails to find their way. Robot drones swarm in much the same way. When humans appear en masse, they're often elated, but sometimes the mood tips over into violence. Swarms change the whole appearance of landscapes. Some are magnificent, others are scary. Swarms are miracles of nature. Some of them especially social and powerful. Many are impressively beautiful and very smart. They have populated the Earth for around 130 million years. 10 trillion ants weigh roughly as much as the entire human race. Every single one toils hard for its colony. For researchers, they are conquerors and strategists. Because ants form powerful coalitions and use aphids as their food supply. They keep order in the forest. Ant colonies are very well-defended democracies. Their trails fascinate scientists who are fond of the finest details. Since 1989, Christoph Klein-Eidam has been researching into how swarms of ants organize themselves and communicate.
Das einzelne Tier ist keine Intelligenz.
Individual ants aren't all that brainy, but they can learn all kinds of things and are amazingly good at getting their bearings. What's fascinating about a colony like this is that these complex structures can be built up through work sharing. And of course, the individual ant has no idea what its nest looks like or how it's structured. It merely acts on the basis of the information it's just received and the experience it's gathered in the past.
In spring, as soon as the first rays of sunshine warm up the anthill, and depending on where the sun happens to be shining, dense cushions start to form. The ants begin sunbathing and heat up their bodies intensely in the process. The thermal image makes this visible. In the blue area, the ant's body temperature is around 10 degrees. In the yellow-orange area, it's almost 30 degrees. Several of these warmed-up workers disappear inside the anthill. They carry their hot breath to the brood and exhale there. Orange and yellow indicate rising temperatures. The warmer it gets, the better their offspring thrive. Ants like these work as heat carriers. They're highly specialized in this one single activity.
This swarm intelligence that we see in fish and birds is reflected once again in social insects, through this individual behavior displayed by single creatures. And that leads to the formation of substructures in the colony. There are specialists and there are generalists, and individual creatures take over the tasks depending on their context.
Ants can carry up to 20 times their own body weight. Some of them clean up especially eagerly. Others briefly exchange information by touching their antennae. And other ants look after their young queen. She will provide for offspring for a long time to come. Leafcutter ants are real long-distance specialists. On the way from their nest to a food source, they can cover around 200 meters, a huge distance for such a tiny creature. And they always take the fastest route back and forth, like on a motorway. That's how they save energy.
For me, swarm intelligence in social insects is the ability to distribute the work among lots of individuals. What's amazing here is that they're incredibly flexible. They're able to respond rapidly to changing environmental conditions and to redistribute the labor.
With a large experimental setup, Christoph Klein-Eidam wants to demonstrate just how cleverly leafcutter ants organize themselves. His assistant Tim uses orange juice to stick tracking marks on food. At the end of an ant trail divided into two sections, the researchers mix the tracking leaves among blackberry leaves, which for leafcutter ants are real treats. Scouts form the vanguard. From their nest, inside a fungus, more ants follow. The researchers' racetrack helps. Just 10 minutes later, the first insects arrive at the destination. An ant trail quickly develops on the long track. The short track to the left of the picture is still closed. Loaded with food, including the tracked leaves, the first ones begin the return journey. The rush hour begins. Some start cutting the leaves. Others immediately drag the fragments away. The more leaf sap fills the air, the busier it gets. So-called hitchhikers protect food and their fellow ants. With all this activity, information starts to flow, about the size of the food source, for example, by means of pheromones, as shown in graphically enhanced super slow motion. Every ant uses these messenger substances to mark its path. Since pheromones dissipate quickly, they all do this, soldiers and workers alike. As a result, they all know where to go. And more blackberry leaves land up at the entrance to the nest. This is how the leafcutters feed their fungus, which serves as their food source. It's definitely efficient. Christoph Klein-Eidam demonstrates the intelligent side effect of the ant's pheromone language and opens the short trail. For a while, the ants use the long trail just as much as the short one. But that changes quickly.
As soon as this short trail here was opened and the first ants found it, the leaf carriers were much faster along this trail. During this shorter time, less of the pheromone evaporated, and this mechanism caused the traffic to shift from one side to the other. Programmers have taken advantage of these components to regulate internet traffic. In other words, wherever the data packets are faster,
the signal stays stronger. Ultimately, that's just what we're seeing here. The data packet here is an ant carrying a leaf.
Ant algorithms optimize entire logistics chain. They make loading and unloading faster. They find shorter routes for transport by truck, or better routing on the railway. They ensure space-saving loading on aircraft and efficient public transport timetables. Data scientists like Heiko Hamann simulate pheromone marking using algorithms. The more often virtual ants take a data path, the more frequently it gets chosen by other virtual successors. Information about processing times and erroneous routes also flows in this way.
The important thing to understand about ant algorithms is that they are only likely to find a very good solution. There are no guarantees. Say something unforeseen happens. A truck driver drops out due to illness, or a crane isn't working today. Then we'd run the ant algorithm again and have to reschedule at relatively high costs. And there, the ants, the biological ones, are maybe slightly ahead of us. Because if something fell on the ants' trail, they'd immediately start looking for a way around it and then find it. So they'd adapt very quickly to the new situation. And the genuine ants could maybe teach us something there.
Ant algorithms are lightning fast at calculating more stable telephone networks and optimizing the internet. And all of it during ongoing operation. That saves time and money, all over the world. But usually it's only the providers who know how the necessary computer programs work. For users, algorithms remain non-transparent. Recommendation algorithms decide on the content that billions of users get to see worldwide. This increases the sales figures of online retailers and makes other swarm systems, such as social media channels, so intelligent. A company's own algorithms analyze which products and videos are clicked, liked, shared, and commented on, and how often. Self-teaching algorithms optimize these processes. But users are also becoming increasingly predictable, without being aware of it. Algorithms have a significant impact on our action.
But that's both a curse and a blessing. On the one hand, it's super practical and convenient if I can find the information directly and don't have to search for ages. But on the other, it can also be a danger if I don't care about it any longer and stop looking around for other information. That might mean I'm sort of caught inside a bubble.
Back to the ant experiment. The leaf carriers are still transporting blackberry leaves to the fungus. And also the leaves with the tracking marks stuck onto them. Like in a relay race, each ant carries a leaf only part of the way, then sets it down. The next leaf bearer uses its mandibles to check the quality of the leaf. Anything that's not up to standard falls by the wayside. It's true that an individual ant is not clever. But within a swarm, ants all optimize the transport route and integrate quality checks.
This means that the decision at colony level is outsourced to these long trails. That way, the very best leaf material gets selected, the best for the fungus.
Using the tracking points on the leaves, the researchers show that during rush hour, all the leaf pieces are laid down several times. The ones that the leaf carriers approve of end up in the nest.
The leaves are solely for nourishing the fungus, and it's only when the fungus thrives that the colony does too. It grows quickly and produces many offspring.
A sustainable symbiosis between ants and their fungus. Without each other, neither could survive. By means of its fragrant language, the ant swarm works with efficiency and high quality, making a leafcutter colony successful for decades. Like a single organism, sheep flow from pasture to pasture. Sheep are frugal, adaptable, and know all about herbs. For 8,000 years, the domesticated descendants of mouflons have been constantly learning and passing on their knowledge to the next generation. Also the way they communicate with other animals, dogs for instance. For conservationists, sheep pastures are treasure troves of biodiversity. The animals maintain our cultivated landscapes, and they communicate all the time. The big ones as well as the very small one. It's just that they do it differently. As a shepherdess, Anna Krüger-Degener has learned to give her sheep more space and to listen to them.
We humans work through synonyms. We have words, the spoken word. We can describe things. We can report from the past or plan for the future. Sheep operate the other way around. They work through spaces and then through gestures. And ultimately, they also have an acoustic language. At that stage, human-animal communication isn't all that ideal and often leads to misunderstandings, to talking past each other. The prejudice that sheep are stupid might possibly be based on that. But it's not true. They just have a different intelligence. It's totally linear and very direct.
Anna works not only as a shepherdess, but primarily as a communication trainer with different types of animals.
Hunde, Datteln, Äpfel, Äpfel.
She illustrates spatial language, as she calls it, with the help of her border collies and Indian runner ducks. The working and herding dogs have to move the flock of ducks from A to B. Anna uses whistles and subtle signals to communicate with her dogs and to guide them.
If you look at the ducks, it's almost as if they have an invisible hula hoop around their bellies, which they use to delimit their own dance area. That's extremely important, so that the animals can survive and no collisions occur. This behavior can be reproduced at any time. It's not trained. It comes out of each individual and each individual character. It ensures survival. It ensures the unity of the group. And we find it in swarms, in herds, and in flocks. We humans have it too, and I think it's the most intelligent natural law there is.
The runner ducks follow fundamental swarm rules. Depending on the radius and angle at which supposed attackers approach, all the ducks dodge, almost synchronously. All the while keeping their distance from each other and orienting themselves towards their immediate neighbors. Their color has nothing to do with it, however. The white ones belong to one family, the black ones to another. Like all sheep, Scottish black-faced sheep can protect themselves better from predators as a group. Their social coexistence is highly developed. From 30 years of working with them, Anna knows that sheep gawk not because they're stupid, but because they are focused. As flight animals, they're extremely attentive. If an intruder approaches, they watch him closely and avoid him. Their defensive behavior is far more extreme than that of the ducks. When working with them, Anna has to take this into account and, above all, calculate it. The angle and the distance of the dogs to the sheep have to be right. If the shepherdess allows the dogs to run in a circle around the flock, she has to be able to stop them at any time and at any point along the line.
The most important thing is that the dogs are amazingly good listeners. They're always in contact with me, and they really enjoy listening and cooperating. At the end of the day, what I'm doing here isn't romantic in any way. It's purely geometrical. It's just that we have this dialogue with each other, and if things get a bit tight in that dialogue, it makes sense to create a wider angle. It's a bit like asking a superficial question, talking about the weather or whatever, to immediately calm everything down again.
A clever way to conduct a conversation. And Anna Kruger-Degener uses it to achieve exactly what she wants.
The moment I stop the dog, there's this immediate relaxation in the flock. That way I can instantly bring any form of dialogue between dog and sheep to a halt and relax the situation.
The communication trainer refers to this as a harmonious principle of spatial language.
This is how dialogue should take place, integrative, so that everyone gets what they need, so that we listen to each other. The dog can convey information to the sheep that I could never convey at all. For that, I need these dogs, the angles, the lines, but above all, the stop. It's only with a stop that I can keep on bringing this calmness into it.
Lambs have to be able to live well with the flock later on, so their mothers teach them important rules. Through play, lambs practice typical sheep behavior. With twins, for example, each twin always drinks on the same side of the other. That way, no one loses out. That side remains the twins' favorite one in the flock later on. Ewes and lambs bond by licking and spreading their own scent with their tails. The intensive bond that develops here lasts far beyond lambing time. Research has shown that family members always recognize each other in the flock later on. Because a single sheep does not weigh all that much, flocks of sheep are especially suitable for organic farming. They compact the soil less, maintaining biodiversity in our cultivated landscapes. Nevertheless, since the turn of the millennium, the number of flocks in Germany have been continuously decreasing by between 6% and 30% annually. Sheep farming has become too unprofitable. These heavyweight quadrupeds prefer grass and clover. Sorrel plants, on the other hand, are something they avoid. The weeds are far too acidic and spread everywhere via seeds and roots. Pastures like these often lie fallow, and for sustainable organic farming in particular, they're a problem. Swarm robotics expert Heiko Hamann and his colleagues are researching into how to help small organic farmers get rid of annoying weeds, without the use of pesticides and without manual intervention. Jackal is the name of the ground robot. Equipped with a stereo camera, laser scanner, and artificial intelligence, it searches for anything that does not belong in the pasture. And in the future, it should be able to do even more.
It could also try to mow along the fences, or just inspect the pasture and tell the farmer if there's anything that needs to be done.
The jackals systematically explore their environment. They are networked with each other and collect data together. Their developers help them to learn, so their database is constantly growing. Whatever gets automatically localized can be automatically removed later on.
Agriculture does feature automation technology, of course, but it mainly involves large machines, large robots, which are also very expensive, and usually they're specifically designed for exactly one task. For a small farm, that's not an option. They need a small robot that's inexpensive, that can take on a variety of tasks, and can be used very flexibly.
The jackals also patrol vegetable patches. Here, they're currently learning what different lettuces look like and how to make independent progress along uneven routes. Once the technology is fully developed, agricultural helpers will never have to bend down again.
Weeding is currently still done manually by people. We want to automate it so that it's done for us by robots instead.
The jackals inform the farmer about what he can harvest when. And because the machines are small and very handy, several organic farmers can share one of the little helpers, or even a whole swarm of them. Some creatures form swarms without any social bond, but they all meet at the same time in the same place. Aggregation is the term used by biologists for this phenomenon. Attracted by the scent of the oriental amber tree, millions of tiger moths meet up every year from mid-June to September in the Valley of the Butterflies. After the rainy season, the entire valley is transformed into a living carpet. Native creatures like the crayfish are happy about such a tasty morsel. And when there are many of them, the loss hurts a little less. This ecosystem is given its distinctive face by lugworm. They eat sand and also excrete it again. This species of finger-thick worm is over 350 million years old, and it grows up to 40 centimeters in length. Over the course of a year, millions of them eat their way through the top 25 centimeters of the tidal mudflat. In this way, their swarm enriches the soil with oxygen. They themselves and other mollusks serve as aviation fuel for wading birds. One reason why masses of migratory birds refuel on the mudflats. On the way to their wintering grounds, they form flocks of mind-blowing dimension. Why is it that oyster catchers move so harmoniously, in unison? In these huge masses, why are there never any collision? For centuries, researchers have been trying to unravel the secrets of formation flying. All that's certain is that the markings on the plumage of some of the wading birds make it easy to recognize any change of direction. For a long time, this heavenly spectacle led to several strange assumptions, also among scientists. Does this exceptional singer know the secret? Starlings can be impressive virtuosos when they sing, but even more so when it comes to formation flying. Every year in autumn, hundreds of thousands of starlings fly from their Scandinavian breeding grounds and make a stopover in the marshland. Charlotte Himmelreich has spent her entire life as a researcher studying how starlings can fly so incredibly close together, how they invent new patterns every second and create these pulsating undulations. Questions to which many researchers have already sought the answer.
Originally there was Edmund Sealis, a biologist in the 1930s, and he studied for 30 years in detail flocks of birds, and he came to the conclusion it can only be telepathy or thought transference, otherwise they can't fly so coordinated together.
He was almost certainly mistaken. So how can the phenomenon be explained? Rome. Many answers lie in the Eternal City. For centuries, it's been a place of pilgrimage. Also for starling. At sunrise and sunset, the show begins. Always close to their roosts. Their current venue? The bus station. Under papal protection, they fill the sky here. It's a sight that Charlotte Himmelreich can't get enough of, even after 30 years of research.
This is super! Oh, it's really beautiful. It's unbelievable, isn't it?
They have also taken over the cemetery del Verano, about 8 kilometers away. During their aerobatic maneuvers, tens of thousands of birds organize themselves like a single organism. How do they organize themselves?
It's a wonder. Starlings do not collide when they flock. And that is because they fly at the exact same speed within a flock. Now just think of it, if we would do that in the traffic, all the cars would drive at the same speed, you wouldn't have collisions. And they stay together by coordinating with each other. And in our computational models, they do so via the 3 A rules. They are attracted to others, they align their heading with others, and they avoid collisions with others.
So, starlings in a flock attract each other, they align their movements with each other, and avoid collision. Physicists in Rome have uncovered some details of this successful secret. Each individual starling only maintains contact with its 7 closest neighbors. He orients himself to them. If one of them changes direction, the others follow. but only for 3 seconds. After 6 seconds, all the neighbors have flown away. A new, different group of 7 adopt the fixed position. Again, only for 3 seconds. In this way, new groups of 7 are formed in a flash. Following this principle, Charlotte Himmelreich and her team have discovered how such complex movements come about, and how those waves ripple through the entire flock.
If the birds are turning, then they have to roll over their shoulder like this. Like you do yourself if you are cycling fast and you want to cycle to the left, you have to roll over your shoulder. If you don't do so, you slip through the corner. But obviously, if birds do this, they roll over the shoulder, then they fall down a little. And if they fall down a little, this means that the flock shape changes, it becomes longer in the vertical direction.
The birds fly at almost the same speed. If they change direction, their position in the flock changes automatically. This becomes very clear when an attacker appears, like this falcon. If he penetrates the flock, the pattern becomes more dense. The starlings change their direction of flight. Near the falcon, things get tight. With the concentrated power of the flock, the starlings practically throw him out. This confuses the attacker. He often has to give up. The starlings also produce black bands. From top to bottom, so-called agitation waves pulsating through the swarm.
And then we tried the second maneuver, which is a kind of skitter or zig maneuver. And in this case, what we do is the birds flee away like this. They make a small turn. And if you see this turn, of course, they roll over the shoulder, so you temporarily see a larger wing area, and other birds close by repeat that behavior. And if we do this, then we see that in the computational model, dark bands move away from the predator. So we think in reality, this is also what underlies the agitation wave, skitter motions of the birds.
The entire starling flock organizes itself. Thousands of birds behave together like a critical system. That's what physicists call it. The swarm is permanently ready to react maximally to environmental disturbances. Do the communicative starlings also exchange verbal information during their maneuvers? It might be a while before that secret is revealed. For this swarm insect too, communication is essential for survival. The honeybee. Even an experienced bee researcher like Jürgen Tautz is highly enthusiastic here.
What we see here are the most important areas in the bee's hive, where a wide variety of activities are carried out. At the same time, that's what's so funny about insects with colonies. They can do all kinds of work at the same time. Each bee must know what to do, when and where. For example, making honey in the honey chamber, or tempering the brood to 36 degrees Celsius in the brood chamber. That's our own body temperature, and so on and so forth. There's a long list of jobs that every bee can do. They're all-rounders. Among insects, bees are really special. They can estimate quantities, up to 4, with no problem at all. That's the performance level of a chimpanzee.
With an experiment, Jürgen Tautz shows just how intelligent bees are.
If you go about things experimentally, it's incredible what you can tease out of these little insects, things that have everyday relevance for them.
On a disc, the bee researcher has hung 4 different faces, with glass bowls beneath them. Only the bowl in front of the face at the bottom left, let's call her Lotta, is filled with sugared water. No sooner are they set up than the first foraging bees are there and drinking from the sweet water. They don't remain alone for long. Jürgen Tautz marks this bee so he can recognize it again. It disappears briefly into the hive and passes on initial information via its antennae. Over the next hour, more and more bees appear. And they all fly to Lotta.
When a honeybee is born in a hive, it knows nothing about what the world outside is like. It doesn't know flowers, but it can distinguish colors. Bees see the world in many colors, except for the color red, which appears black to them. And when bees are out and about, gaining their first experience of flowers from which sweet nectar is collected, then they remember, this is what a flower looks like. This is what a flower smells like. This is the color of flowers.
When a bee fights its way into the light of day, it's the equivalent of a blank piece of paper. It first has to learn the subtleties of its language.
The good old German word Gestalt is very helpful here. Bees learn the Gestalt of objects, that is, their shape, their appearance, their coloring and their size. Bees can learn all of that, memorize it to form an overall picture, and thus recognize any object. And that also applies to human faces.
Lotta's bowl is now empty, and Jürgen Tautz changes its position. Nevertheless, the bees continue to fly to Lotta. They've learned that she has food. Without sugared water, however, Lotta quickly loses her appeal. But how do bees communicate food sources that are far away? How do they find a new home when they've swarmed out with the old queen? For a long time, scientists believed that almost all information was passed on during the waggle dance. The angle at which a foraging bee waggles while dancing shows its companions in which cardinal direction a target lies. The greater the distance, the longer it waggled. But only 9 species of honeybees practice the waggle dance at all, out of around 20,000 species of bee living in the wild. The language of bees seems far more complex altogether.
Communication begins with the waggle dance, as here on the swarm cluster, but continues out in the fields through other forms of honeybee communication, such as flying behind each other. Pheromones are also produced by the bees and released in flight. The further away the source is, the more important a precise indication of location becomes, but the waggle dance itself does not provide that.
Researchers only have a rough idea of the chain of communication for long distances. Scout bees form the vanguard and search for suitable homes, even in areas as complex as forests. If the bee finds an empty tree hollow, it is inspected and measured. It advertises its find to its companions. Some come to see for themselves. The more the bees appreciate the quality of the new abode, the more they dance and advertise for it.
Most bees haven't noticed this at all. Deep inside the swarm cluster, they haven't realized what's happening on the surface. Those familiar with the new home stop dancing, dive in between the bees' bodies, and make a very high-pitched sound with their thoracic muscles.
Jürgen Tautz recorded this sound using a special microphone. The alerted bees react and increase their body temperature. As the thermal image shows, the swarm starts heating up.
This very sophisticated communication between the bees is like the life insurance for this colony.
This is rarely filmed and graphically enhanced. The bees who are in the know emit pheromones via the Nasonov gland, a tiny opening on their abdomen. They use them to lay a scent trail for other bees to follow. The colony swarms out. Around 30 knowledgeable scout bees show the way to 20,000 of their clueless colleagues.
There's an expression about not being able to see the forest for the trees. The forest is the honeybees' natural habitat, so it's quite clear that we have to re-examine their communication. A forest is a space where you have to find your way and get your bearings, and it's so highly complex that many different parallel information channels are needed to guide honeybees to their goal.
If the swarm arrives safely, also thanks to the pheromone trails, the real work begins. By buzzing their wings, the first arrivals distribute their pheromones together. They flutter, and this makes it easier for the others to find the entrance. Then the new home is cleaned and prepared. Some of them form long chains. In honeycomb construction, these serve as plumb line. After a good 3 weeks of work, the swarm settles into the new dwelling. There are many more secrets yet to be deciphered. It's not only bees that use sophisticated communication to access new habitats. The head of a team of experts, Dimitri Schutin, is exploring the environment with swarm systems at the German Aerospace Center.
We used our drones to detect hazardous substances and gases in the air. We've learned a lot from nature, specifically from the behavior of bees. So we're trying to implement somewhat similar strategies and algorithms to teach drones to sniff for possible hazardous substances.
Once everything is set up, the scientists take a back seat. The main role is now played by hexacopters. This swarm flies autonomously and is blind. Gas cannot be seen and often cannot be smelled. The task is to find the gas source and determine its precise location.
The drones use chemical sensors that can measure the concentrations of gases. Those measurements are then shared in a swarm. This data is processed to form the basis of a map, and with each measurement, it becomes more and more precise.
As with bees, it is repetitions that complete the picture. Each drone determines its position coordinates and reports them in real time to at least 5 satellites, which constantly compare the movement data. This means that every drone knows its exact location at all times, accurate to 1 to 2 decimeters. Using chemical sensors, each drone detects the tiniest components of the invisible gas. This data is then permanently shared by all drones in the swarm. So that we can also see what the drones are detecting, the researchers use ethylene glycol. The vapor is clearly visible from a distance. It only takes a few minutes for the swarm of drones to discover the source.
The huge advantage of such swarms is that thanks to sensor technology, they can detect gases, something humans cannot actually do. That's why we think that in the future, swarms like these will be very useful in disaster control, because they can detect dangerous substances in the air and warn people about them.
A brief look into the future. Swarm intelligence poses a major challenge to science. Uncovering its secrets will also help us to protect species. Then, smart swarms will have a chance of survival in the future too.